Okay, good morning. Last time we mentioned our assignment number 3 is due tonight. I think you still clearly remember it. So today is 3rd, 11:59. Okay, to make sure you get things done on time. If you need help, you still can, see me or CTA or put something on Piazza. For program assignment, if you really get some bug, you're stuck there, you can get help from your classmates as well. Okay, hopefully everything's done. And for extra credits, some students ask, how much you may weigh on the extra credit. So I just say, you probably extra credit will play the role if finally you are at the margin. That means suppose you are between A and A minus. Maybe you did it really well on the extra credit. We'll consider some kind of promotion. But normally we don't want to, to add it into the regular grading because we basically is under the same competition. It's more like some students said, I did not so well in the midterm. Do I do a little more work? Give me some scores add to the midterm. We say no, that we cannot do that, right? It's a competition, the test fair to every student. I cannot say you do a little more work, I give you a little more scores. That's not the game. Okay. So you should just make sure you do things in high quality. Okay. We do have assignment number 4, but I don't want to talk about now because you haven't finished assignment 3. I don't want to add more pressure. But assignment number 4 is another program assignment. You need to spend time to understand things and to write programs. Okay. That's the only 2 program assignments in the whole course. Okay. So hopefully you will enjoy it because usually people say you do program assignment, you really play with it, you know deeper rather than just read the papers. I deeply believe that. Okay. That's why you may want to play with this and you learn more about the details. Okay. So then we still continue our discussion on the evaluation or the boosting, our classifier accuracy and the quality. Okay. Last time we said there are so many classifiers, so many ways to do classification. But if you have a way to construct different classifiers, you need to see whether these multiple classifiers or multiple ways to do classification can help each other. Okay. So that's the idea of ensemble. The ensemble basically say, in many cases, we may not just rely on one judgment. We need a group of, classifier working together. Okay. So that's philosophy of ensemble. We discussed there are 3 ensemble methods. One called backing. Backing simply says you have multiple classifiers, or you think about multiple experts. Okay. You want to basically, based on this collection of classifiers, to make a wise decision. Okay. In many cases, you can average them, or you can give different weights on different classifiers, and finally, you may get a better result. That's idea is backing. Okay. Boosting basically is you try to add different weights on your classification methods. Okay. Sometimes you may add different weights, you can retrain it. Okay. So that's boosting. Ensemble essentially is you have a set of heterogeneous classifiers. That means you may use very different methods. One use decision tree, the other use, say, support vector machine or Bayesian methods. Then you try to make collective decision based on the very heterogeneous classifiers. Okay. We first discussed about bagging. Bagging essentially is you take the majority vote based on the multiple or collection of classifiers. Okay. The bagging is very much like you do diagnosis based on multiple doctors' majority vote. That means when you train them, you can say, you train, you get a training set D sub I with D tuples. Okay? Or here, some people actually, after class, ask me, what's the difference between tuple and objects? Okay. We actually, quite often, in this book, we said it's tuple. You go to many machine learning objects, they actually say these are objects. That's the same thing. You can think it's just a tuple is just a one data object with multiple features. Okay. And at every iteration, you train this set. You take a D sub I sample with replacement. Okay. This essentially is bootstrap. Well, I should mention about bootstrap. Most bootstrap method is sampling with replacement. So-called with replacement means you take the sample, next time when you sample it, you still throw your previous sample back to your jar. Okay. Simply says, likely this thing may be sampled multiple times. Okay. Why you do that? Just because when your training data is small, it's a small set. Okay. You don't want to waste any sample. Sometimes even you may say, I have a slight chance to reuse it, okay, in my training. So that's bootstrap, essentially sampling with replacement. That means you can put the sample data back to the jar. Next time you draw it, you still may have a slight chance to draw this previous sample again. Okay. Then, based on this, you can construct a bag of classifiers, means a collection of classifiers. Okay. Then, when you do the prediction, you actually take their average or take their majority vote. You say what should be the class. Okay. So that's essentially the bagging. Here, this particular bagging using bootstrap, we call bootstrap aggregation. Okay. But not all the bagging use bootstrapping. Okay. The bagging could be just a normal classifier. You just build a multiple classifier, ask them to vote, or ask them to give you the confidence you aggregate them. Okay. So that's essentially it's bagging. Then what is boosting? Boosting basically is you not only do this multiple classifiers, you try to learn the weights of these multiple classifiers. That means by consulting these classifiers, you develop your own judgment which classifier should be paying more attention. Okay. This is like at the end of last lecture I said, if you consulting your classmates, okay, but you probably do not put the same weight on every of your classmates. Okay, you probably say, you know, this student likely is an A+ student, this student likely is a C student. You probably put more weights on your trust on this A+ student because you trust this guy likely will give you the right answer. Okay, that's a reason. That's a boosting actually have this philosophy. But how do you get it? Is you based on the training data, you try to work out which one is more trustworthy. That means what weights you want to get. Okay. That means you try to weigh those training tuples or training examples. Okay. Actually, not only you weigh the classifier, sometimes you want to weigh the training tuples. Training tuple means sometimes if I give you a homework question, some are easier, some are hard. Okay. The hard one, you probably will trust more on those very excellent students. They can solve a hard problem. Okay. The easier one, you probably put less weights or something because you say I can handle it, or everybody can handle it. So then you can construct the K classifiers. This particular boosting is actually based on the philosophy of ADA boost. I'm going to show you ADA boost immediately. But I first give you the eta boost, the philosophy. Okay. The philosophy is this. This is very much like your midterm. Okay. Your midterm, some question you say, oh, I got it right. I want to review my midterm for preparation of the final. Okay. I have a limited memory in my mind how I should prepare. Okay. Probably the people will give you a good advice that says, something you did right, you think very easy, probably you don't have to look at it again. Okay. But something you made mistake, you got it wrong. You probably really want to put more weights on this, you learn it. Okay. Then the next time when you do the final exam, you will do better. That's a very good advice. That's actually the advice for boosting as well. Okay. What boosting is doing, you can see this, is after this classifier MI is learned, the weights are updated to allow the subsequent classifier, that means the next exam. You can think this is the last exam, this is the next exam, next time you want to work out the classifier. To pay more attention to the training tuples that were misclassified by M sub I. Simply says, something you did wrong in your midterm. Okay, those questions, you actually want to put more weights in your next round. Why? You can see, because the training tuples you did it wrong simply says you have some deficiency on the thing, misunderstanding or some deficiency. So in your review, you put more weights on this. That means you learn, you say, this one should be this kind of answer. Okay, you learn that you put more weights there. The next time when you redo or you do another exam, likely you will do better. The reason is you put more weights on this. When you construct the model, when you review, you actually will tilt your model somehow to make sure your revision actually can cover this part, right? Can cover something you did wrong. That's the same idea. Okay. Then if you do this, every test, if you adjust your weight, reconstruct your classifier, retrain it. Okay. Likely, finally, you combine all of these, you will get a very good problem solver. Right? So this M star actually is combining the votes of each individual classifier at every time. It simply says, next time I ask people to vote, I ask my previous, the first midterm, the second midterm, third midterm. Suppose I combine these classifiers. Finally, I got my wisdom on all the midterm. But the later midterm, why is also very important because I put more weights on something I did wrong. Okay, then I reconstruct my classifier. I can help solving those tough problems. So that's the same idea. Okay. So this boosting, the whole philosophy is you learn weights from your mistakes. Okay. There's something you did wrong. Okay, put more weights there, you construct a new classifier, likely will solve the previous wrong problem. Wrong classifier caused the problem, right? So that's the whole idea of this boosting algorithm. Okay. Based on this, actually, I think in 1997, Freud and Shapiro, they actually work out an algorithm called eta boost. It becomes very famous. Okay, but that's a boosting algorithm work out for classification and also for numerical prediction as well. Okay. If you compare with bagging, is actually boosting usually is better because bagging you do not know which things is more difficult. You basically, you just get a majority vote. It's more like you think about it. Suppose this patient got a problem, okay? And some problem very easy to judge. Any doctor can make a right decision. But some problem very hard, okay? Only the experts will make the right decision. And after you learn this, you put more weights on these top experts. Then finally you get a vote or get an aggregate solutions better. That's why usually boosting may have better or greater accuracy than the bagging because you pay more attention on those misclassified data, on the difficult cases. Right? So now we introduce this AdaBoost. AdaBoost was first worked out by these two researchers. And at that time, they were at AT&T Research. Or at that time, maybe not even split with Bear Lab. Do not know exactly. But they were at AT&T Research. Actually, Shapiro, when the AT&T in year 2002 or something, they wanted to, that time I believe it was a big mistake. They actually ran out of money. They want to get rid of those researchers, especially they want to get rid of machine learning researchers. That time machine learning was not that hot. They actually disassembled the whole machine learning group. Then those people lost their job. Shapiro actually interviewed in UIC. We gave him offer. But those are very famous people. Actually, he finally decided to go to Princeton. Now I think he's still a professor in Princeton. But you probably can see, of course, now the machine learning is so hot. Probably AT&T really regret because they got the best machine learning group that time in all the industry centers. But they just got rid of them. Okay, of course, those people, they got into other institutes. They play a very important role. Okay. So AdaBoost essentially is, suppose we got a D label data. Like you can think X is your feature vector, Y is your class label. So you get X sub 1 to Y1 to X sub D to YD. You get D training tuples, training objects. Okay. Then at the very beginning, you say everybody is equal. I do not know who is more important. It's more like when you just took the midterm question, say every question weighted just the same thing. I got 10 questions, every question was 10 points. You think they are equal. Actually, they are not. Some questions more difficult than the others, right? So you generate the K classifier in K rounds. Okay? And how do you do it? At the very beginning, you just sample those data with replacement. This is like a boosting. Okay, you sample with bootstrapping. It's a sample with replacement to form the training set of the same size. Then what you do is, at the very beginning, you select it based on initial weight, is everybody weights the same. Okay. Then you construct classifier M sub I. At the very beginning is M1, right? Then you calculate everybody's error rate. That means you get this data sets, you calculate it, one. And you see which one is misclassified. This is more like your midterm exam, which one you did wrong, okay, which one is misclassified. Then you increase the weight. You know the right answer now because you have the label, right? You have the label, you know what is the right answer. You just increase the weight. Say, this kind of problem, I'll pay attention to do this way, okay? Otherwise, you decrease weight. You say, oh, this question is so easy. I probably don't pay attention. Next time, even I judge it initially, I still make it right. Right? So you decrease the weight. That means you calculate this, you get the misclassification error. You have different weights on the error. This is WI is your, W sub J is your weight. Okay. This XI is your feature. XJ is your feature. You base on their error weights, you get a new, calculate the error. Then you can go, you basically go back again. You put more weights on the things you did wrong. Okay. Then you get in another round. Of course, they randomly sample. It's not exactly the same training data. It's a different training data. But that kind of feature, you use since you know the error rate, you put more weights on anything goes wrong, you learn better. Okay. Basically, after many rounds, finally, you can weight all the classifier in the final voting. Simply says, if the original one, you put a little, because of the, you originally your weight, you can, based on this one's weight, you actually take the log, you put different weights there. Essentially, you put more weights on the later one, then you will be able to get a very good classification. Okay. I think actually even in our homework number 4, the programming assignment. I think the TA put this ADA boost in your implementation as well. Okay, you probably, that forces you to read not just the slides, you read the book, you can read the original Shapiro their paper. Okay, so this is a very classical, very famous algorithm in machine learning. So that's why originally the TA think back and forth still want to put this one in the assignment. It simply says, you really want to read it and implement it, you feel it. It's a very influential algorithm, yes. I see. Yeah, the question is whether next round the error will always decrease. Actually, you can never guarantee that. The reason is, remember you do the sampling. Sometimes, for example, the first time you may not sample into a very tough problem. You correct it, you go down there. The second round when you sample, you may sample something really hard. It's more like, of course, here, the midterm, you only try one. If you do the Coursera course, we actually require the TA to prepare a set of questions. Then the students actually take a sampling for those questions. So sometimes it's by your luck. You know, you may, the first time you took the exam, you may sample either question. The next time you take the exam, you may sample a tough question. So even you made it very well in the first exam, but the second time you sample into a really tough question, you may reduce your score. Right? So there's no guarantee. But overall, since you pay attention on the tough problems, overall you can trust later you may do better. But because the data is different, you can never have a guarantee the next time you definitely will get a better score. Right? So even sometimes people take like a GRE score, they took it 3 times, not necessarily the last time will get a higher one. Sometimes they may even reduce the score. Right? So that's the same idea. Then we get another very interesting method called random forest. Remember, actually, last time we discussed decision tree, we give you a rainforest. Okay, even they all call forest, they are completely different. Okay, so sometimes I even give exams, say distinguish rainforest and random forest. People really look at it and get confused. What is rainforest? What is random forest? Rainforest forest essentially is the scalable decision tree one, right? You basically get the ABC set, right? You get a very compact ABC set. You can do, you scan data once, essentially you can make a decision to which tree to select. Right? So that's rainforest algorithm, developed by Johannes Gerke in Wisconsin, later in John Cornell. But random forest is a completely different one. Actually, this random forest was proposed by Breimann. I think he was in Berkeley, year 2001. Okay. Actually, Leo Breimann got ACMC KDD dissertation, the Innovation Award. The Innovation Award is an award to a person who got overall technical contribution is the best. People get a vote. Unfortunately, he got this award. He was very ill already. The time when we really get to the award ceremony in the KDD conference, he already passed away. Because he was critically ill when I was on the evaluation committee when we all voted for him. And at that time, we also know he was critically ill. We want to give him the award before, something happened. But he got information, got notice. He was very pleased. But he still could not last until the KDD conference. But anyway, he was a statistician and made a lot of contributions. But this random forest is one of the very famous contributions he made. And the general philosophy for rainforest essentially is ensemble of a decision tree classifier. Okay. But the difference is, if you strictly follow decision tree, you only get one tree because you use, suppose you use information gain. Okay. You compute, you will say this attribute put on the first choice. After splitting the next remaining data, you pick up another attribute as a second choice. You split tree, you only get one tree. Okay. Actually, this random forest, the value is on random. That means I do not require you construct a very good tree. Okay. That means you even do not have to use the information gain compute to get a best splitting point. You can randomly pick out any attribute as your splitting point of constructed tree. Okay. So that's why it's random. Okay. Then you may say, you just thought, you said you want to construct good tree, you really need to select the best attribute to put on the top you split. Now you change your mind. You say randomly you can pick one to split. Okay. The reason is this. Even you pick up the best one, because you pick one at a time. Sometimes 2 or 3 getting together, you may make a really good decision. But you pick any one, they are not so good. Just give you a simple example. In hardware design, you know there's an exclusive OR function. Exclusive OR means these two getting together, 1, 0 getting together, you get a very good decision. But you pick any single one, you get a very bad decision. So you may not even want to pick it, right? So that means if I have a bunch of exclusive OR-like attributes put together, your decision tree will make a very wrong decision because you look at each one and say, no, this is a junk attribute. Forget it. Okay. And you do not know when they combine together and make a so clear decision. Okay. Decision tree is pick one at a time. So you will never pick either one of them because they are exclusive OR, right? So that's actually happens sometimes. You may make a 2 or 3 getting together. They make a really good decision. You use information gain. You do not rank either one of these attributes high. You miss the chance. Okay. So what they do, random forest said, I'm a little flexible. I can randomly ask anybody on the top. I generate many, many trees. Okay. You may say, oh, your tree may not be that smart. So what? It's more like you think about doctors. Okay. If you say, I pick the very best doctor to check whether I got a cancer or not. The doctor sometimes still make mistakes, right? But if I have so-so doctor, I have a lot, but they all both say I have no problem, I probably would feel more comfortable. Maybe I really have no problem. Right? Even this very best doctor may say, I'm not sure. Right? You're still comfortable because there are so many doctors. Okay. That means sometimes 3 or 4 poor doctor probably can be better than a really excellent doctor, right? So to that extent, this is a random forest philosophy. Random forest, you can construct many trees, okay, in a little random way, but you still do the splitting, you still make decisions, right? So you may have this random forest, you still have the training data, you still split according to the training data, so overall it's not that bad, right? Then you get many, many such trees. You ask them to vote. Okay, so in many cases, some corner cases, you originally did not put in because they do not have that many support to support this. You still got the right one. So in that case, they shout together. Okay, they may make really smart decisions. I actually, in the next chapter, I'm going to introduce you one. Actually, it's our own PhD student generated one called DP class. The random forest, how many trees he worked out? He worked out in the tens of thousands of trees. Okay, it's just not 1 or 2 trees. Work out tens of thousands of trees. But finally, he can construct a very compact classifier in a very high quality. The classifier has very high accuracy. But the final thing he picked up the one is so compact. It means from 10,000 trees, he finally picked up the rules. It's just like 20 rules. Okay? And you can get very high quality. Simply says, you use random forest, you need probably lots of trees, but getting together still make very good decisions. Okay. So this is the idea. So you generate many trees in the classification. Of course, that the student is not doing this way, but in the real random forest is in the classification, every tree will vote, and the most popular class is returned. Okay. You probably know the general election, you get millions of people, hundreds of million people vote, okay, make a joint decision. And so that decision is, you can think it's a little like a random forest, because so many people will vote. Finally, likely you get a better one. Right? So that's what we hope, right? So that's why the general election is very popularly used in many countries, because it's very much like a random forest, right? But getting together collectively, you may make a better decision. So then you can. There are two methods. Actually, there are more, but in many textbooks they show two methods. One called random input selection, RI. One called random linear combination, called RC. Okay. Random input selection means you randomly select at every node, you select F attributes as candidates for split. Okay. That means you got this node you want split, you randomly select the F attributes. The F is still a small number. Remember, your total attributes still could be very big. You randomly select F attributes as candidates to split that node, then you generate multiple trees, right? And random linear combination is when you create you try to create a new attributes, a new features as a linear combination of existing attributes. That means you are not just rely on these attributes. You actually create a new one. But how to create the new attributes? You get an existing one, you do the linear combination. That means you say this one weights twice than this one. Okay, then you do linear combination. You can do this, right? Actually, I think even in election, you probably also see that. Like Democrats, they have called super delegates. Right? Super delegates means those delegates not from every state. There were some people originally in Congress or in Senate. They probably hold some kind of ticket. They call these as a super delegate, right? So this you probably can think is some kind of attribute. Combine them, you get a new attribute. And that attribute will count in the splitting as well. Right? So this is random linear combination. Usually this one, if you get numerical data, you get linear combination, probably will make a lot of sense. Okay. So actually their experiments their accuracy is comparable to ADA boost. Remember, this one is not boosting. You are not weighting different trees. Okay? But of course, later you can see people really develop things. You can weight different things. But it's more robust to errors and outliers. Why it's more robust? Like we said, you're not relying on step-by-step to carefully check each attribute. You just let everybody to play. Okay? Then those side corner cases, somebody will cover. That's why usually it's more robust. Okay? Actually, if your training data is small, your real case is very big, many people like to construct random forest because you may cover something you did not see. Okay? Just give you a simple example. We actually work out phrase mining. You did assignment 3, you did some kind of phrase mining. We actually construct a phrase mining called sec phrase. Okay? That phrase mining algorithm have very tiny training examples. How many examples? You get a gigabytes data to try to work out many high-quality phrases. What they require is the 300 labels. I mean, 300 positive, 200 positive, 100 negative, or 100 positive, 50 positive, 50 negative. That the case is the training data is very small comparing with gigabytes data. Now, how to use this training data? Actually, the best algorithm is the random forest, because there are so many phrases you've never seen. You only pick up 150. Okay. And very likely you will miss many, many other cases. So you try to make sure it's robust, it covers better, so you use random forest because you almost like everybody to play. Right? So that's random forest. So it's very popular used in both in machine learning, data mining, and statistics. So that's why Breiman, got this algorithm. He got his name there as well. Then we discuss another one called class imbalance data set, how to do classification. Okay. Actually, this class imbalance is very popularly encountered. You just think about this, okay? You got you see a doctor make cases on the cancer or non-cancer cases, right? So the data they got, actually the majority data is no cancer. Okay. Only very small cases is really cancer. So if you pick up a population, you pick up lots of samples on even the tissues. Suppose you say this guy is somehow suspicious to have cancer. They may get some sample. Even the sample that really have cancer one may still the minority. Okay, the majority is still no cancer. Okay, because people want to be conservative, right? It's better to say no rather than say sorry. You really have it. Right? So that's a case likely will look like this picture. Because so many samples, they actually have no problem. They are negative. Okay. Then you get a small set, they are positive. That's your labor data. The labor data has very small number of data is positive, like this is cancers. The majority one says no problem. Okay. It's negative. You get this, how do you construct a good classifier? Okay. Remember, majority classifier we want to construct, we almost give you even, like a 50% positive for 50% negative. Okay. You almost get even cases. It's more like in the presidential election, when you do sample, you probably want to sample somebody vote for Trump, somebody vote for Hillary. You want to get a reasonably even sample when you construct the sample or classifier. Right? You don't want to get a majority. You go to Trump camp, you try to get a classifier. Likely you will do something wrong, right? So, but you got the real case is in medical science or in many other cases, like anomaly detection. You got a very small number positive. And how can we do good classification using this case? Okay. These are several popular use methods. One called oversampling. What is oversampling? It means these are the rare cases, the small set or rare set of positive data. You want to use this one repeatedly. That means these are small set of cancers data. You want to take this as your teacher repeatedly. Say, these are the cancers, right? So how do you take repeatedly? If you want to random sample, you want to do biased sample. How bias it? You say, every time you have to pick up something from there. Okay? And the remaining thing you can be a little random. That's called oversampling. That means you actually, for example, you want to get a here it's only 4. Actually, the best case is you almost sample all these 4 possible cases. Then you sample the remaining one. You really randomly sample 4. Then you get 4 over 4. Okay, that case you construct classifier. Maybe it will be more fair, right? Because it's somewhat even cases you work out the sample. That means the next time you do ensemble, or you first pick this. You randomly pick the 4, then you pick the 4 again. You randomly pick the other 4. Then you construct a classifier. Likely, the classifier will be more trustable. Okay. Then another one is undersampling. That means you have so many positive data, negative data. The negative data you want to do is undersampling. That means if you say, 80% sample on this positive data, you may only do 10%, 5% sample on the negative data because you want to make the final training case is somewhat even, right? You can undersample this negative data. Another one called threshold moving. Threshold moving means, originally you say the cutoff threshold is right in the middle. But now these underrepresented, like a positive case is so small, you want lower down for this case, you will lower down the threshold for this one, you raise the threshold for the other one. Okay. So those usually we call threshold moving. That means moving your decision threshold to the rare case, easier to classify, you have a less chance for the false negative error. You basically, it's a threshold moving. Then another one called ensemble technique. Ensemble means you really get a multiple classifier, you ask them to vote. Okay. Actually, I got one PhD student, now she's a professor in University of Buffalo already. Okay. Got a really, really strong case. And she worked out for stream classification, data stream. And she want to find outliers. Okay. That's exactly the same case. Is you get an anomaly come like intrusion. So you capture those intrusions is very rare. You capture them, it's very rare. But the data coming like the water, right? So sometimes you catch this one, then the next bag you catch this one. Then how could you do good classification? She actually worked out exactly the same philosophy. Is every time capture the anomaly, you stay there. And those negative data, just let them go. Then once you get now, you need to make a decision. You basically take the current data. All the previous anomaly cases, she already reserved them. And she took all these as oversample, took the whole thing. Then she picked up the current data, majority are negative. She picked the current one doing sparse sampling, but sparse sampling every time sample almost same size as a positive group. Positive set group. And the anomaly capture all of them. Suppose it's 20. And here you get 1,000. What do? You just pick every one, same thing. And she builds multiple classifiers, then find her ensemble. And she made a very fast algorithm and also very accurate. So that's, she published this paper in one conference. I think it's really good work. Basically, it's almost use all the 3 or 4 methods here combined together. Okay, so then made a really smart classifier. Okay, so now I should say we give you the general philosophy on classification. Even I haven't got a chance to touch very advanced classifier yet, but you know the philosophy already. Okay, so it's very important. We know we have decision tree, Bayesian, and many others, and we also know how to evaluate them, how to use bagging, boosting, ensemble to help them, or even you get a rare classes or something you can handle. Right? So that's lots of very good research papers. I probably would say you need to go to even a lot of machine learning textbooks. They discuss lots of this. Okay? Data mining, of course, they discuss this, but I think a machine learning textbook would probably treat more thoroughly on this part because they, like a machine learning course, they spend almost the whole semester on the classification. So this one is, I took a picture in Australia. Okay, you probably see those are the, with so many millions of years, the water actually eroded all the coast, and but they left something here down. So it's a very, these are all the trees, actually really huge ones. And I was told the picture here, they originally have 7 or something. After a visit around 2003, I saw the newspaper said that the one big one actually collapsed because so many years, right? You know, this is millions of years, the nature work, right? Okay, so now we finish the chapter 8. Now we get into chapter 9. Okay, that's one still on classification, but we claim this one is more advanced methods. Okay. But even advanced methods, I will not get into very details because the advanced methods are so many and quite deep. Almost each one can be a course, can be an independent course. That's why I only give you some hand waving. If you really want to learn it, you have to go down to individual courses. Okay. So this is the, everybody knows, I think if you've ever been to Chicago to to Lake Michigan, around that area, you'll see this. There's lots of people taking pictures. Okay, so I probably should give you a general philosophy what we did, okay, what we are going to do. We were first introduced Bayesian belief networks. This one actually is the starting or prelude of a very big field called probabilistic graphic model. If you ever been to Coursera CEO, Daphne Collar, was a professor in Stanford. She was the top expert on that. She wrote a book. It's that thick. Okay, so almost one semester nobody can cover it. So, but people pick up some chapters, cover it. It's very deep, very, very mathematical. Okay, but if you like to learn it, you should take the Coursera course. She made, as a CEO, she made her course completely open to the public, okay, so you can learn it. Then the second one, neural network. You probably heard deep learning. This is the starting point of deep learning, and it's very deep. Okay, so you probably can. I was told that deep learning good textbook is just going to come out in December. Okay, we don't have a good textbook yet. My research group, quite a few students asked me to book it, even now pay to Amazon. Once they release it, we are going to get it. Okay, so that's neural network, deep learning, very, very hot topic. Support vector machine itself is another course. You can see it's a very, very deep one. So all the three ones, I even just cover a few slides. You know, there's a whole course back it up. But I cover in a very shallow way. Okay, so you just give you a little idea. That's it. Okay. Unlikely I will test you very deep because this is more like a conceptual. You know the concept is. The formulas, all these, I probably say you have to go down to those sites to get the real formulas. But anyway, it's a very rich domain. There are many, many things. But we are going to give you more like an overview instead of going very deep. Okay. The first thing is about Bayesian belief networks. Okay. Actually, this one somehow started with the Bayesian theorem. We know that. And you also learn naive Bayes. Naive Bayesian algorithm, basically you assume all those attributes are independent. Then you can construct a very simple classifier. But people may say, how dare you claim they are all independent? Of course, in reality, they are not. Okay. That's why people become more serious, say, if I want to do better, I have to say they are not independent, I have to deal with them. How to deal with them? They construct this Bayesian belief networks. Okay. Actually, for Bayesian belief network, also called Bayesian network or probabilistic network. Actually, going further, they get this probabilistic graphic model. That's exactly, they get into the whole field. So, but they start from here. Okay. Actually, most people popularly used is this example. Say, you know not everything is independent. For example, you want to judge whether this case is a lung cancer case. What do you judge? Actually, there are several things, several attributes determine whether you will get lung cancer. But in the meantime, they are also somehow independent, but not really independent. That means they really have some mutual dependence. Okay, just give you a simple example. You look at lung cancer, you may say it determines one thing is family history. That means your family got this long history, have this kind of cancer. Likely the gene may pass to you, right? Another one is a smoker. If you smoke, you regular smoke, the chance to get lung cancer is very high. So they take this as the two major factors. But smoke may get other problems. And the other problem may get, for example, you spit, you may get something, they can check inside, they can find some dirt things or germ or something. So they get into all these, and if you do X-ray, lung cancer likely to get a right X-ray, but in the other case, it's maybe X-ray will not show up. Okay, so those are the cases. And what they do, this patient, is they work out the probability on every edge what's a chance to get it. Okay. For example, For this lung cancer, we call LC. Not lung cancer is not LC. Okay. So then this FH means family history. This S means smoke. Okay. So you probably can see, if you say, if this case is both family history and smoke, the chance to get cancer is very high, it's 0.8. Not getting is only 0.2. But if you have family history but not smoke, you get 0.5. Okay, the not getting lung cancer is 0.5. Okay. But you do not have family history, you smoke, you get 0.7. But you are none of them. You don't have family history, not smoker, the chance is only 0.1. Of course, this case is I do not know if it's real or not, but at least they discourage you to smoke, right? So that case, they say this one is conditional probability table, or CPT. Okay. What they have, what the whole thing they want you to play is this table plus this graph. Okay. This graph is, they call this one is probabilistic network. The real probability is shown in this picture, in this table. Okay. So that means what is your graphic model? Essentially, it's this kind of directed graph. For directed graph, you have certain dependency you draw as a links. Okay. Then you say these are the parents, X, Y are the parents of Z. Z is a descendant of X and Y, like this. So then you assume there's no loop, no cycle, okay? Because this the probability just from here, this probability determine the other one. So this kind of directed network we call probabilistic network. Okay. Now you can see how you do reasoning. Okay. This one is another popular network. It's very similar to your, just see the family history. This is a fire. You get a smoke. Or you get a fire alarm. But if you're tempering the alarm, you also get alarm. Right? So there are chances you can see. You get alarm, there are two cases. Smoke, there's another case. Once you get alarm, people have to leave. So you get people have to leave, you get a leave. And you have to report. So you get, this is the whole case. Okay. Then based on this case, you can say, for example, for whether you get alarm or not, you can work out this probability graph. That means if it's smoke, you get a fire. If you get a fire, what's the chance to get smoke? You get this probability. And if you get alarm, what's the chance you get a fire? What's the chance you get a tempering? You get this probability. Okay. Of course, you probably can see, even there's no smoke, no fire, no tempering, you still get alarm. There are cases because the alarm may malfunction, right? So you get 0.001. Okay, the chance is very low, but you get all the cases covered. So then, once you get this conditional probability table, you can work out the real condition by time up, multiplying all those probabilities. You multiplying all these probabilities, you actually can have a conditional probability. You get more conditions, you work out like a long chain. People call these chain rules, right? But anyway, what you need to think about is multiplying all these probabilities, you get a final income, the final probability on all the possible cases, right? So with this, people actually try to construct such a network because in the real case, people give you this network. Of course, you can do something. But a very challenging thing is how to get it. That means you get a real case, how to get it. Actually, the case is, people say there are several cases you can get. One case is person. You just write it out. You just draw the picture. Okay. You say, based on my experience, the alarm have these two cases. You draw the picture. While you draw the picture, you can, based on lots of real cases, you can work out the probability. That means the conditional table may be based on lots of cases to work out. But who links with who, what's the reasoning likely has to be done by human. Okay, so that's the case. A lot of people say you do subjective construction. That means based on your common sense, you work out this picture. Okay. And while you work out the picture, you can, based on the training, you may work out it. Suppose you get this graph. Based on the training and testing all these, you can work out the table. Okay. Another way is people work on using Markov assumption. Markov assumption basically says you get this case, what's the chance going out, what's the chance to come in. You based on this, you can work out a they call hidden Markov model. Using hidden Markov model, you may be able to work out the cases. Right? So another one is you can learn from data. That means it's really using data mining, you can construct the graphs. Okay. Actually, if you see there are lots of people doing this, it's based on data mining, they try to construct it. I can give you interesting cases. I just read a paper from Stanford. They have a computer science group led by Chris Ray. They have a bio group led by Russ Altman. Okay, those are all big names, big professors. Okay. They work together. They try to construct what they call protein-protein interaction network. This actually, of course, is not exact Bayesian network, but it's similar philosophy. Okay. How they work out, they say there are so many proteins. You probably know there are so many proteins because any amino acid, they get together, they can work out a protein. But they can work a very long one. You get a 20 amino acids. You think about 20, you work out the 2 or 3, you get a 20 times 20 times 20. What about the chain 1,000? You get 20 times 20 to the power 1,000. There's so many cases you can get a new protein. So the protein-protein interaction is very, very many. How people work it out is biologists try to say these two protein, they interact. They based on experiments. They work out this graph. But there are so many new ones. Okay. Not everybody can contribute to the graph. It's incomplete. What they do is they say, we mine the researchers' literature. There are lots of journal papers on this. They try to mine the text, try to work out this protein-protein interaction network. That's exactly, you can say, learn from data. It means you, from the text data, you see this protein mentioned together more times, so you try to check whether it's positive or negative or something, you work out it. They mine from the text data, get this. So this is learning from data. To get this kind of network is still a systematic, challenging problem. That means you learn from data is still pretty difficult. There are lots of, like a natural language processing, anything can come in. Right? And so David Hackerman, he was a professor, I think, in SRI, Stanford Research Institute. Later, he joined Microsoft Research. He's quite famous in Microsoft Research. I think he's a lead on machine learning group currently in Microsoft Research. In early days, he wrote a tutorial on learning with Bayesian networks. He laid out these different scenarios. One scenario is keep both network structure and all variable observable and compute only the CPT entries. Simply says, you give me a network. You give me all the variables you can find. Then you just say, compute this table. This is the easiest case. Because you give me the network is clear. Okay. The second one is network structure is known. Some variables hidden. That means I actually miss some variable I do not know. But you still can compute. How you compute it, basically his suggestion is gradient descent, or you can say greedy hill climbing method. That means you try to optimize this function, you see which variable give you the best optimization, give you steepest climbing or dropping. And you take that one. Okay, then you draw those edges. So those are called gradient descent, and try to work out some hidden variable, then you get enrich this web structure. That means the weights essentially is randomly initialized. Okay. But at every iteration, you try to find the best solution, and you adjust the weight, and finally you can work out this. So this is the second scenario. The third scenario is network structure unknown, all the variables observable. Okay, that means you know all the variables, but you do not know structure. Then what you do is you search through the model space to reconstruct the network topology. That means you try to find, you know this variable, you say whether there should be an edge, how strong this edge should be. You base on those variables, their correlation. You may work this out. But then the scenario 4 is unknown structure or hidden variables. And what he said is, nobody can solve it, right? So you have to give me a lot of information I can construct a trustful one. Either you know the structure, or you know a lot of variables, their data. If you don't give me this, I have no way to do it. Okay, so basically, that he gives this 4 scenario. Essentially, try to construct this Bayesian network is a big challenge. That is an important problem. But of course, how to do the reasoning, you should go down to Daphne Coller's big book. Okay. I do not know which professor in this campus is teaching this. I know our department head, Rob Rudenbar. He was a hardware person, but he taught this probability graphic model using Daphne's textbook at least once. And he said he spent lots of hours learning and then teaching. Okay, so it's a kind of a hero because nobody there to teach it. It's so thick book. But he was the first one tried, at least reasonably quite successfully, I was told. The students really like it. The second one is neural networks. Okay. Neural networks, let me see whether oh yeah, it's here. I probably should start with this one. Okay. But I probably should say, nowadays, everybody knows neural networks because everybody probably heard of deep learning. How many people did not hear deep learning? At least you heard deep learning. I think everybody heard deep learning. So what is deep learning? Actually, deep learning, if you go back to the history to look at this so-called neural network, this philosophy, it was not new. Actually, the earliest philosophy you can trace back to 1940s. That means in the 1940s, people starting constructing this kind of a nonlinear, sort of like neuron structures. Okay. Even that time, there were no computer yet. Okay. But in 1980s, people actually used neural networks to solve problems already. But somehow in around 1980, the people actually call that's the time is AI winter. I cannot say exactly AI winter, but for neural network, that time it was a real winter. Okay. Why? Because the neural network can solve some problem, but one thing is neural network construction, the scale you can solve is very small at that time. And the computer power was very limited. Then you just cannot solve a very large, very real problem. Of course, the research did not reach that deep as well. Okay. So people are thinking this is just playing the toy. Okay. And even now you do the deep learning, you need a very powerful, like a GPU, like lots of things. Like Google even compute this for days to get something out. Google has, of course, lots of machines, lots of GPUs. So it does take a lot of computation power. So that's the reason that time it did not fly. And here, I think 2005 to 2009, that's several times. Every year, those pattern recognition, computer vision to do the competition. And around the year 2009, I think, 2009, 2011 has a few competition. The winner, the top several winner are all these deep neural network. That actually shows a very tough problem they can solve so nicely. And the computation power was not a problem anymore. So people really embrace this and become very hot. And they found more and more problems can solve using this methodology. So it's really boosting. Now everybody try to find deep learning experts. Okay, it's not like that time. Okay. So, but we can go back to say, what is neural network one. I probably should change this one because originally we got a subtitle is classification by backpropagation. But I probably should say neural network instead of this because nowadays even people using neural network, not necessarily everybody doing backpropagation, but they still doing various kinds of neural network, just different learning methods. Okay. The general philosophy for this backpropagation is you construct a network, you need to train. How do you train them? Actually, neural network, the general flow is forward. It's not backward. Forward means you start from the input, you get an input layer, then you go through the hidden layer with different weights. You go through the hidden layer, you go to the output layer. They go this way. Okay. All the flow, input to outflow, is forward. But why call backward propagation? Because you do forward, you propagate down to the output. Sometimes you did wrong. Okay. There are training cases. Training cases say you did wrong. Okay. Once they claim you did wrong, you have to adjust the weights on all those edges. How do you adjust? You propagate this. You propagate like an alarm, a training. You did wrong, something wrong, you go back. You go back, it's layer by layer, go back to the very beginning layer. Then you readjust the weights to make sure this weights, finally you go back, made it right. Okay, make this training data. You match the training exam labels. You did it right. That's why you propagate the error to the back. You adjust your weight. Then you redo it. You make it right. So that's why they call back propagation. Okay. Actually, the neural network always go forward. So let's look at the very beginning, the very simple neuron. Okay. Very simple neuron is very simple in the sense, neural network, they start thinking about a human or any animal. The brain contains lots of neurons. Those biologists already found it. But the computer scientists or biologists did not know how it works. They just know things are connected. Okay. So that's why neural network, some people call this as connectionist, because you think all the neurons connected, finally some magically you can think, you can speak, so there must be some neuron connection play the role. But people did not know how neuron works. Okay. The computer science did not know either. The computer science called this neural network just thinking about all these neurons are connected in a complicated way you can learn. That's why they get it. Actually, they were not really simulate neuron performance. Because the real neuron, the neuron fire, they go all the directions. There is no starting ending point. Okay. And this one, they do have input-output layer. They do have starting ending point. They go in that one direction. That's different from the real biological neuron. But actually, because they are connection, so they still call this one neural network. But remember, this electronic neural network and the biological neural network are very different. So then we look at this neuron. This is just a one neuron. Okay. The whole neuron there are many. Okay. They connected together as a network. This single neuron, how it works, you can think this way. You get a bunch of input. Like you get n input, x0, x1, xn. Here, this one actually is not really another layer. Okay, what it's saying is, I probably should not draw this like a layer. This one just weights. That means you start from x, you go down to this part, you have a weight. Say x0, you have a w0 as weight. xn, you have wn as a weight. Your input, this n inputs never changes. But the weights can be adjusted. Okay. Then here, there's a function. I wrote down sigma, say weighted sum. Actually, in reality, it can be many different functions. For example, you can use sigmoid function. You can use many other functions. Okay. I just give you a simplest one, just to say sigma. Okay. And how do you really do the function? The function could be just a mathematical function in the electronic neural network. It's just a mathematical computation function, like this one. This is signed sigma, this kind of function. Very simple. But you have a bias or threshold, let's say mu k, this mu. Then the function could be this. You get a weighted sum of all your inputs, Then there's a threshold or bias, mu k. You sum them up and minus your mu k. Okay. Then you get a sign. Sign say positive, you return this output say positive. Then sign is negative, you return is negative. It's more like classification, binary classification, positive and negative. Of course, in many cases, this may not be signed one. It could be the real numerical function, like a computer numerical value, especially if this neural network is used for regression or for clustering. Then the one output is not a plus minus. It's a real value. So, and this essentially is your activation function. So you're basically using this one to compute the whole thing to generate the output. This is just one neuron. Okay. And if you think about this vector, this is a multi-dimension. It can be many dimensions. It depends on this, right? Now we look at the many neurons work together, you form a network. Okay. Network, of course, this is one way to write it. Many people write this way. Okay. They write it. This is the input layer. This is the hidden layer. This is the output layer. Okay. Of course, you can write this. You have to say, this is the input layer. This is the hidden layer. This is the output layer. Either way. Okay. So then this input layer, you have a connection to the hidden layer. Okay. Not necessarily everybody connect to everyone, but if you get a complete one, is every neural network connect to every hidden nodes in the hidden layer. Okay. But by learning something could be the weight is 0, essentially it's not connected, right? So you can think that way. Learning different weights, you can compute. You essentially may not connect some nodes. And then the hidden layer, you will also connect it in a complex way, connect to the output layer. All these ones contain the weights. Okay. The trick or the learning of neural network essentially is learn those weights. Okay. For different tasks, different training example, you finally compute all the different weights. And the training could take a long time because sometimes you get thousands of iterations. That means you train it, you get another example, you get a bunch of examples, they train it. They go back and forth. Essentially, it's go back and they do back propagation, they adjust the weights, they train again. And finally, after rounds and rounds of training, they say, this network is trained. It can be used for example, recognize the 6 or the 10 digits, or can recognize the pictures, or recognize the voice. Training takes a long time. But once it's trained, you use it, you can be instant. Okay? So that means when you really make judgments, say whether this is a car or whether it can recognize your voice, nowadays a lot of a voice recognize, like you leave some message to your phone. They can translate even to English. Okay? You think it's magic, they translate, sometimes the quality is not bad. Actually, many of these training was done by neural network. They listen to your voice, they can translate right away. Okay, so that's the trained neural network. Training takes a long time, but using it instant. Okay. Next lecture, we're going to discuss a little more on this. Okay, thank you.